in a place when there is any liquid or gas is there, if you actually pass, you illuminate with a light, some part of it will be scattered in the same line, but a small fraction, very, very small fraction will be scattered with a deflection. And that's far less intense than the original, the other scattering which I am talking about in the same wavelength.
You don't get to know objects simply by shining a light on them. It's the color, the scatter, that truly reveals their character. This was the crux of Sir C.V. Raman's life and works. An experimental investigation into the identities of atoms revealed in color signatures of their scattered light. This was an investigation so strong and important, it won him the 1930 Nobel Prize for Physics in record time of 2 years after its discovery, the first for any Asian scientist anywhere. Raman was, in fact, a full-time civil servant by day, but his after-hours research at public laboratories of the Indian Association for the Cultivation of Sciences yielded 27 published papers in the first 10 years.
C.V. Raman, he was actually very much interested in science. However, there was no opportunity. He came originally from Tiruchirappalli, Trichy, which is currently known, and then he had his subsequent education in Madras, which is currently known as Chennai. His father prompted him to write the civil service examination, which he performed exceptionally well, and he was posted in Calcutta. And there he was posted as an accounting officer. He came here in 1907. One day he found that there is a signboard which says that Indian Association for the Cultivation of Science. It was so close to his heart because he was always aspiring to do science by himself. So he got down and he wanted to know whether he could be given an opportunity to practice science, whether the laboratory would be accessible to him, and so on and so forth. And he was very glad to learn that this would be available to him. Subsequently, he used to make routine visit every day after office hours and before office hours, few hours, and even in the weekends. That's how he used to make use of the facilities to satisfy his scientific curiosity. But in the year 1917, Calcutta University, that time the Vice Chancellor was Sir Ashutosh Mukherjee, he decided to set up Science College to start science in a big way in Calcutta University. And he inducted C.V. Raman as a chair professor. So actually that time Raman left his job and accepted this position of a Palit chair professor in University of Calcutta in Science College, almost at half of his remuneration that he was receiving in the Accountant General Office. Because his science was so close to his heart, he wanted to utilize that opportunity. And rest of the thing is all in the folklore. We know that subsequently he went on doing more intense research. He used to do teaching in Science College for his earning and do research in Indian Association for the Cultivation of Science.
Like all things worth dedicating a lifetime to, Sir C.V. Raman's pursuit of interaction of light with matter started with a poignant observation. How scattered light can contain wavelengths that don't feature in the light originally shown on the objects, and why? On his way back from England, aboard the SS Narkunda in November 1921, Raman noted in his diary, The view has been expressed that much admired dark blue of the deep sea has nothing to do with the color of the water, but is simply the blue of the sky seen by reflection. Whether this is really true is shown to be questionable by a simple mode of observation used by the present writer, in which surface reflection is eliminated and other factors remain the same. It was a letter meant for nature titled The Color of the Sea. Raman had a new insight to offer, but first, as an experimentalist to the core, he had to verify his views in his laboratory in Calcutta.
Now I am going to demonstrate the Raman experiment in a simple way. So here I am using a Nd:YAG laser. This is 532 nanometer laser. Now passing through a liquid which does not absorb the green light. So you can see the green light passing through the liquid. The scattering you are seeing here, this is Rayleigh scattering. So you cannot see this Raman scattering in bare eyes. So if you want to see that one, you have to put a filter that can actually block the original laser light, the exciting source. So you have to block the exciting source first, and then you can see the Raman light. If you want to block this light, you need a special filter which can block this 532 nanometer laser light. So this is a special type of filter. You can put in front of it, you will see the Raman line through this filter like the red light. But if you take out this filter, you will see the green light only. This is the Rayleigh scattering.
Surprising, fresh and evident. Raman and his student Kariyamanikkam Srinivas Krishnan went on to report their experimental findings to Nature in a paper titled A New Type of Secondary Radiation.
His observation was that irrespective of the sample that you take, you always get a secondary emission. It's a very weak emission, but that time these laser lights were not available. So what he did, he used a big condenser. Condenser means that it's a very big lens, and the sunlight that was used to condense the sunlight, and then he used these different kind of these optical filters. So changing these optical filters, although the sunlight is a perfect white light, you can generate your desired color. So what Raman did, that using the desired or different kind of these filters, he got colors of different wavelength, and then he focused those light on different kind of samples. So what he used mostly that different kind of these organic liquids. What he published in his first paper that appeared in Nature in 1928, that about 60 organic liquids he used. And it is not only that the liquids that is available in this industrial form, he was very much able to purify that liquids in a best possible pure form. And then he observed that irrespective of this liquid, when a particular color was shine, and then he always see that the same color of the secondary emission. So then he was very curious in the sense that the fluorescence is a process that is known at that time, that it depends on the material, because if the wavelength of the light doesn't match with this absorption wavelength of this material, one doesn't see the fluorescence. But this is such a situation that irrespective of the material, he can always see the secondary emission. So that's why first he termed this phenomena, and this is a very feeble fluorescence, feeble in the sense that this is not a normal fluorescence. So the first Raman spectrum that was reported in Nature, so it is basically taken from that paper. So he reported that time the spectrum that was given is from this benzene and this toluene. So these two spectrum, this Raman spectrum, he recorded for the first time using his own home-built apparatus and the mercury lamp that he acquired at that time from one of these European company who first brought this lamp in the market.
Professor Robert Williams Wood of Johns Hopkins cabled Nature to report that he had verified Raman's brilliant and surprising discovery in every particular. This very beautiful discovery, which resulted from Raman's long and patient study of the phenomenon of light scattering, is one of the most convincing proofs of the quantum theory. In his 1930 Nobel Prize address, Raman remarked that the character of the scattered radiation enables us to obtain an insight into the ultimate structure of the scattering substance. Niels Bohr, in his recommendation letter to the Nobel Committee for Physics in January 1929, validated the Raman effect by stating that this phenomenon, the explanation of which agrees so well with the quantum theoretical ideas, will undoubtedly become a most important source in increasing our knowledge of the state of atoms and molecules of matter in transition, between which the characteristic spectra are emitted. In the first 7 years after its discovery, the Raman effect had become the subject of more than 700 papers in the scientific literature.
So in India, the 28th February is celebrated as the National Science Day because on this day in the year 1928, Raman first publicly announced the discovery of his discovery, that is this Raman effect. Now, in the year 1998, the American Chemical Society, they identified this Raman effect as one of the important discovery. So that's why this term it is called here this international historic chemical landmark. Because that time Raman himself, he realized that his discovery will have a very tremendous impact on the analysis of the various chemicals.
From my recent work, I have seen that Raman spectroscopy can be put to a lot of use in our recent researches, especially for my kind of system, which is two-dimensional magnetic system, and it's a very novel system, and probing it otherwise is quite difficult. But Raman spectroscopy helps us to probe it in an indirect way to find the transition present in it or the different type of coupling mechanisms.
Raman spectroscopy gives us the information about the layer numbers. Here, from the difference of the two Raman peaks, you can get the layer number.
So IEEE identified that the Raman effect, it is one of the important discovery in electrical engineering and also in the computing. So that's why they came here and they gave this particular plaque that you can see here, that it was given in 2012. They came to ICS. Now the importance is that in most of the times in this optical signal communication, when optical fiber is used, and if the laser light is passed through this optical fiber, then what happens that particularly this silica material, from the silica material the frequency is shifted. So this shifted frequency that usually causes, it delays, it reduces the intensities of the transmitted signal, and not only that, it has been observed that this shifted frequency of this optical fiber can also be used or can be exploited, this particular phenomenon, for transmitting the signal through optical cable at different frequencies.
The significance of the discovery speaks for itself. As Raman concluded in one of his 1928 talks in Bangalore, we are obviously only at the fringe of a fascinating new region of experimental research which promises to throw light on the diverse problems relating to radiation and wave theory, X-ray optics, atomic and molecular spectra, fluorescence and scattering, thermodynamics and chemistry. It all remains to be worked out.